Hey guys, welcome to the video that talks about empirical formulas and the calculations that we do with them. Let's get started. Previous video talked about percent composition and the difference between molecular and empirical formulas. Just as a reminder, empirical formula is the lowest common multiple of the molecular formula. Empirical formulas are important because it enables us to identify compounds experimentally. In the lab, usually what we'll find is the empirical formula of a compound, and we can backtrack with calculations to find the molecular formula. So they're really important to be able to go back and forth between them. Given the percent composition by mass of a compound, and we know how to do that, but given the percent composition by mass of a compound, we can determine the empirical formula of the compound. And since we're dealing with percentages and the sum of percentages is always going to be 100%, it's convenient to assume that we started with 100 grams of a compound. So it's an assumption that we're going to make in most of these problems. Here I'm showing you figure 3.5, which is on page 86 of your book, and it sort of gives you the step-by-step process of how these problems are going to go. So you're given a mass percent, and you're going to go ahead and convert those percents to grams. Just directly convert them to grams. And then you're going to divide each of those elements by their molar mass. You're going to find the moles of each element, and then you're going to divide by the smallest number of moles. Once you do that, you actually get the mole ratio of all the elements. Once you find the mole ratios of the elements, that's essentially the empirical formula of the compound. We're going to do this step by step, so you'll see it's really easy. We just have to keep practicing. The first problem says determine the empirical formula of a compound having the following percent composition by mass. Potassium, 24.75%, manganese, 34.77%, and oxygen, 40.51%. In the lab, we found that this theoretical compound that we've been studying has these percentages. I want to be able to find the empirical formula of this compound. The first thing I do, since I have a percent, and I know that this compound, all these elements are going to have to add up to 100%. So I'm going to go ahead and convert them to grams. There's no conversion. We're just going to assume that it's out of the compound out of 100 grams. There's that many grams of each element. So since there's 24.75% of potassium, that means there's going to be 24.75 grams of potassium. I do the same thing for manganese, and I do the same thing for oxygen. Now, and also please note that all of these percentages do add up to 100. They have to add up to 100 for this to actually make sense. And they will. They always will add up to 100. So now I have all of these elements in grams. What I'm going to do is convert them to moles. You always convert them to moles first, because that is how you find the smallest integer ratio of a compound, not through grams, only through moles. So you get the grams and you use the molar mass of each of them to convert each of them to moles. So 24.75 grams of potassium. What's the molar mass of potassium? It's 39.10. So 39.10 grams of potassium on the bottom, because it has to cancel with the grams on the top, and that's equal to 1 mole of potassium. That is the molar mass of potassium. Molar mass can only be over 1 mole of that element. Okay, so 39.10 on the bottom, grams of potassium on the bottom, 1 mole of K on the top. I do the same thing for the other ones. There's 54.94 grams of manganese and 1 mole of manganese, and there's 16 grams of oxygen in 1 mole of oxygen. I calculate all that out, and you see that you get 0.62399 moles for the potassium, 0.63287 moles for the manganese, and 2.5318 moles of the oxygen. Now what you got to do is, since everybody's in moles, you have to divide by the smallest number. So you look at all of the elements and you figure out which one's the smallest amount. The smallest amount is going to be the potassium. So I go ahead and do 0.62399 moles of potassium divided by 0.62399 moles of potassium. Obviously that's going to be 1. Then I go to the next one, 0.63287 moles of manganese divided by the moles of potassium. That also gives you around 1. And then I do the same thing for the last one, 2.5318 moles of oxygen divided by the moles of potassium. And if you do that, you should get around 4. Now you're ready to put the empirical formula. The empirical formula would be K, and there's 1K, and we don't have to put the subscript when it's 1. We assume that it's 1. So just K, and it's also going to be Mn, just 1 Mn, and then 4 for the oxygen. So the empirical formula of that compound is KMnO4. So that's called potassium permanganate, and that is the answer. It's really simple. So again, you take the percentages, you convert them to grams, from grams you convert them to moles, and then once you're in moles, you divide by the smallest one, and then you figure out what subscripts need to go into the empirical formula. So chemists often want to know the actual mass of an element in a certain mass of a compound. And because the percent composition by mass of the element in the substance can be easily calculated, the problem can be solved really fast. And for example, we'll do this problem. Calculate the number of grams of aluminum in 371 grams of aluminum oxide, Al2O3. So I need to find the number of grams of aluminum. But what information do they give me? The only information they give me is 371 grams of that compound. So I'm going to start with that. 371 grams of Al2O3. To get to grams of aluminum, I have to first go through the mole-to-mole ratio. In this compound, I've got 2 moles of aluminum. So I have to first get to moles of aluminum by itself, not 2 moles of aluminum. So the way that I do that is I have grams of aluminum oxide. The only way to get rid of that is you have to divide by the same unit. So we have to find what the molar mass of aluminum oxide is. If you add everybody up, 2 aluminums and 3 oxygens, you're going to get 101.96 grams of aluminum oxide. Now I have the same unit on the bottom. So I put 101.96 grams of aluminum oxide on the bottom, and that is equal to 1 mole of that compound. And then I'm in moles of aluminum oxide. I have to get to grams of aluminum, but before that, I gotta do it through moles, right? Mole to mole ratio. I know that in 1 mole of aluminum oxide, there's 2 of them. In that compound, there's 2 moles of aluminum. So see, you can make relationships between moles, and that's the only unit that you can make relationships. You can't do that with grams. So in 1 mole of aluminum oxide, I have 2 moles of aluminum. Now I can go from moles of aluminum to grams of aluminum, which is what they want. So in 1 mole of aluminum, there's 26.98 grams of aluminum. If you notice, I have gone ahead and set up the entire problem, making sure that everything cancels out. And by everything, I mean all the units. The units are the most important when you do these problems. The units have to cancel. If they don't cancel, then you've done the problem wrong. So just make sure you understand this process. So if I go ahead, I'm done. I'm at the unit that I need to be, grams of aluminum. So I just multiply and divide everybody out. You'll see that you get 196.34 grams of aluminum. Keeping in mind our sig figs, it's actually 196 grams of aluminum. Okay, let's do 1 more. Actually, maybe 2 more. Okay, a sample of a compound containing boron and hydrogen contains 6.444 grams of boron and 1.803 grams of hydrogen. The molar mass of the compound is about 30 grams. What is the molecular formula? What we've been doing so far, or what we did in the first problem, was we found the empirical formula. What's cool is that from the empirical formula, you can actually find the molecular formula. So that's really what the process of this problem will be. We're going to find first the empirical formula, and then we're going to do 1 extra step and find the molecular formula. I'm already in grams in both of those elements, so I don't have to convert from percent to grams anymore. I'm already there. So I just go from grams to moles. I do 6.44 grams of boron, 2 moles of boron using the molar mass, and I go from grams of hydrogen to moles of hydrogen using the molar mass. If I do that, I get 0.5961 moles of boron and 1.78869 moles of hydrogen. I'm in moles of all of the elements now. So I do, obviously the 0.5961 is the smallest one, so we're going to have 1b, right? Because 0.5961 divided by 0.5961 is 1. And then I'm going to do 1.78869 divided by 0.5961. That gives me more or less 3. So my empirical formula is BH3. Now we're at the step to find the molecular formula. There's several ways to do this, but the way that I do it is once I get to my empirical formula, I figure out how much that empirical formula weighs. In other words, find the molecular mass of that compound. So I have 1 boron and I have 3 hydrogens. If I add those up, that empirical formula compound weighs 13.834 grams. They tell me that the molar mass of the compound is about 30 grams. So the molecular formula weighs about 30 grams. So all I gotta do is say, okay, well, if the molecular mass weighs about 30 and this empirical formula, I just added it and it weighed about 13, well, divide it. I would say 30 grams of the molar mass divided by what the empirical formula weighs, and that gives me close to 2. These are approximations. When they say it's about 30 and you have a number that's close enough, I think we got like 2.16, that's close to 2. Okay, so that means that the empirical formula fits into the molecular formula 2 times. So since that's the case, that means that you have to multiply the empirical formula by 2. Each element of the empirical formula, you have to multiply it times 2. So the actual molecular formula is B2, because 1 times 2 is 2, and H6, because 3 times 2 is 6. And go ahead and verify that. If you do 10.81 times 2 plus 6 hydrogens, you're going to get around 30 grams. Okay, I'm going to do one more, and this is actually problem 3.44 in the back of your chapter, and it reads peroxyacyl nitrate, abbreviation PAN, is one of the components of smog. It's really bad really bad compound. But anyway, it is a compound that has carbon, hydrogen, nitrogen, and oxygen. We need to determine the percent composition of oxygen and, that's supposed to say and, the empirical formula from the following percent composition by mass. And then they give me all the percents. Once we're done with that, then I need to find the molecular formula given that the mass is about 120 grams. I hope you notice this is exactly the same type of problem. The only thing is now they want us to find the percent composition of oxygen. Well, the compound has 4 elements. They give us percentages for 3 elements. So easy, right? We got to find the percent composition of oxygen. Well, that's super simple. Do 100 minus 19.8 minus 2.5 minus 11.6. And whatever's left is going to be the oxygen. So if I do that, it's 66.1% oxygen. So this compound, PAN, has 19.8% carbon, hydrogen 2.5%, nitrogen 11.6%, and oxygen 66.1%. We need to find the empirical formula. Convert all of the percentages to grams. Now we're in grams. We can't do any comparisons with grams. We have to convert them into moles. So same thing for step 2, convert everybody to moles. Grams of carbon to moles of carbon, grams of hydrogen, moles to moles of hydrogen, so on and so forth. If you do that, you get 1.65 moles of carbon, 2.48015 moles of hydrogen, 0.082798 moles of nitrogen, and 4.13125 moles of oxygen. Third step, figure out which one is the smallest number of moles, and that's the guy that you divide everybody by. Obviously, it's going to be the nitrogen. So if I divide all of the elements by nitrogen, the empirical formula that I get is C2H3NO5. That is my empirical formula. Now I have to find the molecular formula. Given that the molar mass is about 120 grams, what I need to do is find the molar mass of the empirical formula first to figure out how many times the empirical formula fits into the molecular formula. So if I do that, that's 121.034 grams. Well, guess what? The empirical formula only fits once into the molecular formula. So the empirical formula is the molecular formula. So the answer to the molecular formula would be the same compound, C2H3NO5. All right, guys, I hope this has really helped. This is not hard in any way. You just have to make sure you practice and keep practicing the problems in the back of the chapter. And once you're done with that, go to Google and find practice problems, because the process is always the same. It really is. I hope you've noticed that from this video. It's always the same. You just need to know that process so you can have it in the back of your hand. All right, thank you so much for listening, and I will see you guys later.